Murdulata Chowdhury, and my NAC is MC2827. My topic is Cook's theorem. Cook's Levin theorem. Definition. So the definition of this theorem includes a language L which is said to be NP complete if the language L belongs to NP and for any alphabet A belonging to LP and A less than or equal to L. NP complete is non-deterministic polynomial complete. Now the theorem can be described by satisfiability if NP is complete. In computation theory, the Cook-Levin theorem or the Cook's theorem states that the Boolean satisfiability problem is NP complete. That is, it is in NP and any NP can be reduced in polynomial time by a deterministic Turing machine to the Boolean satisfiability problem. The theorem is named after Stephen Cook and Levin. So this is how the definition of Cook's theorem is. Proof or the main idea. So the main idea of Levin theorem works in this manner. Let A be a language from NP. Then there is a polynomial time non-deterministic Turing machine NT. So there is a non-deterministic Turing machine for a polynomial time. Now for every input x for NT, we build a propositional formula of a symbol x encoding the computation NT of x such that satisfying assignments to the symbol correspond exactly to the paths in NT of x. If the symbol is short enough and can be constructed in polynomial time, we get the required polynomial time reduction. So the main idea is to construct a symbol in polynomial time, and this polynomial time should be short enough so that we can inquire the polynomial time reduction. Assumptions about NT. Assume that NT uses h plus 1 symbols such that lambda of 0 to lambda of h, where lambda of 0 is the blank symbol. K plus 1 states such that Q0 to Qk, where Q1 is the accepting state. L instructions such that R1 to RL, which is distant possible transitions. We need to assume this about the non-deterministic Turing machine. Now, assume that every part in NT of x has a length x. We can extend every shorter path assuming that no further action is taken. We can cut longer paths because they make no difference whether x is going to be accepted or not. Now, we assume that the tape head never moves to the left from the leftmost symbol of the input in a Turing machine. So these are our assumptions about NT. Variables. Now coming to variables, we use Boolean variables to specify exactly the possible configurations of the machine at each time such that t is less than or equal to t star is equal to x within A. Now here are some descriptions of the variables as shown below. P of I s comma t is true if and only if sth cell contains symbol lambda of I at a time t. Now there are h plus 1 dot x of them. Coming to the second variable, q of I to the t is true if and only if nt in state qi at a time t. There are k plus 1 dot x of them. Coming to the next symbol, which is s belonging to s comma t, is true if and only if tape head on sth cell at a time t. There are x power a dot x power a of them. Coming to the symbol r t to I is true if and only if the machine implements instruction Ri at a time t. There are L dot x of them. Formula. Now, the formula for the Cook's theorem can be described as below. A says each cell at a time t contains exactly one symbol. So, the formula and their particular variables and their descriptions are given as below. This is the formula of Cook's theorem. Conclusions. Now, coming to the conclusions, we can construct a formula in the symbol in polynomial time. Note that the construction is only possible in principle since the A will not necessarily be known. If formula in symbol is satisfiable, then the variables of the values specify an accepting computation for x. Conversely, if there is an accepting computation for x, then the corresponding values for the variables will satisfy the formula. Hence, x belonging to language, which belonging to symbol belonging to language of satisfiability. This is the Cook's theorem, hence proved. Thank you.